Okay, so Leetcode practice time. So in this video there are two goals. So the first goal is to see how to solve this problem. So we are going to find the solution, and we are also going to do some coding work. And the second goal is to see how we should behave in a real interview. So let's get started. So in the real interview, the first step is always try to understand the problem. If there is anything unclear, please bring out the question, and at the same time think about some edge cases. So let's take a look. So critical connection in a network. So there are n servers numbered from 0 to n-1 connected by undirected server-to-server connections, forming a network where connections I is equal to AB, which represents a connection between server A and B. So any server can reach any other server directly or indirectly through the network. So critical connection is a connection that, if removed, will make some server unable to reach some other server. So return all the critical connections in the network in any other. So let's see, the example is like this, and the critical connection is 1, 3. Alright, so let's see some constraints. It says n is between 1 to 100k, so it's never going to be an empty graph, and connection start length is n-1. Okay, and connection I0 is not equal to connection I1. Okay, and there are no repeated connections. So what if there is only one node? So if there is only one node, essentially there's no connected there's no critical connections, and actually there's no connections. That's the only edge case I can think about currently. And also I think it is worth mentioning that what if the whole graph is not connected? So for example, if there are some separate, let's say if there's no such edge within the graph, what will happen? So in that case, since the graph is not connected, so it doesn't bother for us to find the critical connection because the original graph was not connected. So those are the only things I could think about as edge case. One is only one node, and another thing is the input is not connected. So let's assume that the input is for sure to be connected, the graph is for sure to be connected, that's the assumption. And also, let's say n-1, I think it should be covered by our general algorithm actually. So other than that, I think we should be good to go to the next step. So the next step is about finding solution. So how to solve this problem? So of course you can try to remove each of the edge, and then do DFS on top of all the options. So for example, you remove this edge and then you do DFS to see if the graph is connected. So it's similar to like finding how many finding how many islands, etc. Like similar, very similar questions. But for that one, the runtime is going to be horrible because it is essentially let's say there are v edges, and it is going to be v times so it is going to be v times n. So let's say there are n nodes and v edges, so it is going to be v times n. So that's a profile solution. So another optimal solution, I did a search online. So it seems like there is some textbook algorithm which is called Target algorithm. So for that one, it is going to result in v plus n as a runtime. So let me explain how the Target algorithm works. So essentially you have you define three different things. One is called the DFN, this is an array of integers, and it is a number of the nodes, and also a low thing, and also it is a parent. So all those three arrays are with length n is the number of the nodes within the graph. So the DFN means so for DFS, you know that each time we have a timestamp. Like we have so for DFS, it's like, for example, if you start from here, then you go to here, then you go to here, and go to here. So like if you start from here, let's say the timestamp is 0, then the next call, if you go the next call, which is one level under it, so the timestamp for this, let's assume is 1. Let's assume the timestamp for to call this node is 2 and this node is 2. So that's essentially what the timestamp is, and this is essentially what the DFN is. So it is more about the timestamp. So let's call it timestamp though. Timestamps. So this is a timestamps for DFS. And also there is something called low. So what is low? So let's say we start from this point, and we traverse the graph. And okay, so let me explain the parent first. So parent. So let's say I start from this node, and then from the function we go to from the DFS function we go to this node. So the parent 1 is 3. So it's like the parent relationship within DFS. And similarly, the parent of 2 is 1, the parent of 0 is 1 as well. So the next thing, low, which is the most important thing, is the low means suppose so for some graph like this, so without going through its parents, what is the earliest node we could try to reach? So for example, let's say we have this graph, and suppose there is an edge between 0 and 3, and we start from this node 3 to traverse. So the parent of 1 is 3, the parent 2 is 1, the parent of 0 is 1 as well. So let's say there is an edge between 0 and 3. So without going through the parent of 0, which is 1, we could easily reach out 3, right? So the timestamp for 3 is 0 because we start the DFS traverse from 0. So since there is an edge, we can set 0 to be we can set low 0 to be the same timestamp as 3. So the definition of low is without going through parent, what is the lowest timestamp of some nodes it could reach out. So that's essentially the definitions. So this brings down to how much we understand about DFS though. So for those 3 arrays defined here, if we understand DFS pretty much, then I think we should be able to fill up the whole things and then finally get the answer. Okay, so after we fill out all of those things, the condition to decide whether it is a critical connection is, suppose there is an edge between U and V. So if let's say the edge, let's say it's the parent relationship is something like U and V. So U is a parent of V. So if low V is larger than the timestamp U, then this edge, the UV, is a critical connection. That is because we know the definition of low. So since low V is larger than timestamp U, then it means there's no way for the node V to reach out any of the previous nodes that comes before you without going through you. So that's essentially the principle of how the algorithm is going to work. So having said that, let's do some coding work. So for code, we care about the speed, we cared about the correctness of the code, and also we cared about the readability of the code. So let's give it a shot. So I would say the first one is always try to build some graph. Let's define a helper function. Let's call it build graph. So the graph, I would define it as integer to set of integer. Let's call it build graph. So for build graph, we are going to pass in the actions. So it would be integer on set of the integer graph as equal to new hash map. So we are going to go through every edge. So integer edge connections. So we have from node as edge dot get 0 and 2 as edge dot get 1. So because it is undirected graph, so we need to build the edge from 2 and from to 2, and then another edge from 2 to from. So it will be something like if graph.nice key the from, then we are going to set graph dot put the from new hash set. So graph dot get from dot add 2. So similarly, we are going to build the reverse way. So if not graph dot contains key 2, then we are going to have graph dot put the 2 and new hash set, and then graph dot get 2 dot add the from. And finally, after we build the graph, we are going to return the graph. So here we just simply call the graph is from build graph for the connections. All right. So the next step is about initializing the timestamp, those 3 arrays, and also call the DFS stuff. So let's say we have the timestamps. So new int, and we have the low. Let's call it. So low is a bit. So let's say call it earliest timestamp. Just call it earliest. New int, which makes more sense than the low DFN stuff. And we also have the parent relationship. So let's call it timestamps, earliest, parent. And also we will need to define the final result to be returned. So let's say this is a list of the integer connection. So let's say critical connections, new so new linked list. All right. So another thing I think I want to define is a visited. So we have, let's say, set of the integer visited new hash set. So you're going to have the int I is equal to 0, I smaller than n, and plus plus I. So if we have already visited this, yeah, so if we have already visited dot contains the key which is I, then we are just going to continue. If the visit already contains a node, then we are just going to continue. Otherwise, we just call DFS on top of, let's say I, and also the timestamp. Let's say it is starting from 0, and timestamps earliest, and also the parents, and also we need to have the graph passed in as well. We also have the para connections. Alright, I think that's pretty much it. Let's define another helper function, and finally we need to return critical connections. This is critical connections to be passed in. So you're going to say this is void. This is void, and DFS. So this is let's say the ID, and this is a timestamp. This is earliest. This is called timestamps. Say this is earliest. This is the parents. This is the graph to be passed in, and the last one is the critical connections, which is this. Yeah. So at the very beginning, we will need to set the timestamps as equal to timestamp. This timestamps ID, and also we have the earliest as the timestamp as well, and also we will mark the visited. Okay, so we also need to have the visited to be passed in as well. So this is a set of the integer visited. We will have the visited dot add this is ID. Okay, and then the next thing is we go through all of its neighbors. Let's say int neighbor. This is graph dot get ID. So all of its neighbors. So if the visited stuff, if it doesn't contain the neighbor, so which means it is the first time for us to visit this neighbor node, what we are going to do is we are going to set the parents relationship. So parent.neighbor is equal to the ID, and then we are going to call the DFS stuff on top of it. So DFS, let's say this is neighbor and timestamp plus 1, and then the timestamps earliest, and the parents, and the visited, and also the graph, and also the critical connections. So if after this is returned, what we would do is we will see if the lowest, if the lower stuff can be something smaller. So if okay, so let's say lower ID is equal to the smallest one between current lower ID and the lower neighbor. Yep, so this is the lower ID. Okay, so, and we will say if the lower it's not lower, it's like we call it earliest. So if the earliest of the neighbor is even larger than the current timestamps of the ID, which means the neighbor node cannot reach any of the node that comes before ID, then it is a time for us to add the edge as a critical edge. So we are going to have let's call it add edge, void add edge, say from, and this is int2, and this is the critical connections. So you're going to have this helper function. Let's implement later. So it is going to be ID to the neighbor, and also the critical connections. Alright, so after that, I think we should be good for this branch. So if the node is something we have already visited, so if it is a node that's already visited, then first of all we need to make sure that it's not its parent node. So if neighbor is equal to parent's ID, then we just simply continue. Otherwise, if it is not the parent, then what we would do is we will need to set the earliest of so the earliest of ID is equal to mass.min earliest ID and the timestamps of the neighbor. Yeah, so that should be pretty much it, and let's implement the add edge function. So integer edge is equal to a new linked list edge.add from edge.add to, and the critical connections add the edge. Alright, so that's pretty much it about this code, and the next stuff is for us to do some testing. So for testing, usually it goes through sample test case, explain how it works, and also do some sanity check about the logic, fixing the bugs. So let's depend on this IDE to help us fixing some typos, whatever. So it is line 89. Okay, so it's a typo here. So 40. Yeah, so this is mass.min earliest. Yeah. Alright, so it is wrong answer. Why it is the wrong answer? So we should output as 1, 3, but currently we are getting the 0 and 1. So let's see why. So first of all, we build a graph. Let's see, we have the graph here, define all the edges from the connection from and to, and then if it doesn't contain from, then we are going to okay, so it's something like this. I think we didn't build the graph right. So we are going to add from to and to from, then we return the graph. Alright, so I think after we fix a bug, that's good. Let's submit it. Yep, so it's accepted. So as I said, this is a very textbook algorithm, so I don't really think it is a very suitable way to put it as a coding question, but if it happens, it is better for us to be well prepared about this algorithm. So it is a very well known algorithm in graph. So personally, I don't like it, but please be prepared about this question. So that's it for this coding question. If you have any question about the algorithm or about the solution or whatever, feel free to leave some comments below. If you like this video, please help subscribe to this channel. I'll see you next time. Thanks for watching.